Hello there. Now we're on to the third section. This one's about the law of conservation of energy. This one's kind of a big one. This is going to be your bigger questions. Is going to all come from this unit. So pay attention. This one's important. It's not like all the other ones are unimportant, but this one is like the big mark questions is this one, combining everything together. So we need to understand the law of conservation of energy. We want to solve some problems. Surprise, surprise, that's no longer new. Okay, here's the law of conservation of energy. Energy cannot be created, nor can it be destroyed. It is only changed from one form into another. That is the big thing with conservation of energy. You cannot create or destroy energy. It's only transferred from one thing to another. So you can imagine a boom slug jumping into the air. Here we go. Now in this process, energy cannot be created or destroyed. So as the boom slug is traveling upwards, its kinetic energy is being converted into potential. So at the bottom, kinetic, and at the top, potential. And then as it travels back down, that potential is now converted back into EK, like this. So this is why, if you remember from projectiles, the speed or the velocity of an object going up is going to be the same as the velocity when it comes back down, just in the opposite direction. It's because of this principle. So when only conservative forces like gravity are acting on an object, we have that this kinetic energy is converted into potential and potential is back to kinetic, like I said with the boom slug. When you've got non-conservative forces, say friction, that's the main one I think we're going to deal with this unit, then you have energy not being conserved. So friction converts some of this energy into heat and we lose it. Now at the end of this unit, we're going to see how we can still incorporate that into the conservation of energy, but for now, we're going to deal with only conservative forces, otherwise it'll get a little bit tricky at this point. So here's an equation for conservation of energy. Essentially it says energy initial equals energy final. You don't lose any. Now I can expand this into the different types of energy I've shown you. So initial kinetic plus initial potential equals kinetic final plus potential final. And from there we can plug in the specifics for EK and EP into this equation and get this nice big long equation. This is what we're going to be using in order to solve questions involving conservation of energy. Like I said, this is a combination of all the stuff we've learned so far. So if we've got a calm slug that's starting from rest and sliding down an inclined plane, as you see, we can try and find its speed at the bottom of the incline. Using the equation I just gave you, initial energy equals final, expand it out into this form. Now we can take a look and see which of these cancel, because sometimes stuff cancels out. So if they start from rest, my initial kinetic is 0, and at the bottom of the incline, we have 0 potential, because it's at the bottom, my height is 0. And another thing we note with the leftovers, we can cancel out masses. Plug in some numbers, solve for VF, you get 7.27 meters per second. All right, so this example, we've got an inhibitor slug riding on a roller coaster, as you can see here. If its speed at the second peak, so the 35-meter peak, is 18 meters per second, we want to know what's its speed at the first peak. So again, we start with EI equals EF. We expand it out to this. Remember, we can set our 0 point for potential energy wherever we want. We can set it at the ground, we can say it's the table, and depending on where we set its 0 point, the height will change relative to that point. So to make our lives a little bit easier, let's set the 0 point at the second peak. How this helps us is our final potential energy can now be 0, because that's at their 0 height. And our initial height we'll just need to set relative to this green dotted line. So from here to the first peak, our initial height will be 15 meters. This just makes it so that we can cancel out this final potential energy. Now you don't have to do that. You could still use the heights of 50 and 35. You'd still get the same answer, but this is just something to make it a little bit easier. Again, we can cancel out all the masses because each mass is the same for each term. So plug in some numbers for this and then solve for V initial equals 5.48 meters per second. So that was its speed at the first peak. Notice it was smaller because it's at a higher height. You have more potential energy than you have kinetic energy. So there you go. This is the conservation of energy law. Again, this was a combination of everything we learned. I will expand on this at the very end of this unit and add one more component, but these are your big mark questions, is having all of these, all the potentials, all the kinetics, and trying to solve for something with that. So here's our next clip. This one's from Fast and Furious 6. Hey, do you notice a pattern? I'm doing a lot of Fast and Furious movies. There's a reason for that. Yeah, so this one, we are doing the final epic battle, whatever you want to call it, for Fast and Furious 6. So if you haven't seen this movie, spoilers ahead. I'll show you the clip. Tell me what you think. Yeah, so I'm not going to play you the entire clip because it's like 13 minutes long that they're just continuing to drive and chase after this plane, and there's a fight on the plane and all of that. I don't need to show you it all. Really, the main thing with this one is it takes 13 minutes and they're driving at that speed for the entire 13 minutes. So if we're looking at this, they're driving, they're going high speed, they're chasing the guy gets on the plane, they're still driving after the plane because it hasn't taken off yet. And so for the whole 13 minutes, they are just chasing after this plane at what, like maybe 120 kilometers an hour or something like that. So yeah, it's gonna take quite a while. They need a really big runway, and obviously there's not a runway that's that big. I heard a stat that I think the longest runway is like 3 miles, something like that. I don't do miles, but like 5 kilometers ish, and there's no runway that's big enough to be able to have this entire chase fight scene in it.